Hello everyone. In this video, we'll continue to discuss the process data, the data processing, and the final graph, okay, so the linearized graph. It's worth noting that most of the advice for this is actually better taken and more directly taken in the videos on the Excel processing for the Acceleration Due to Gravity Lab, also available on YouTube. But in any case, you should have a separate data table that corresponds to your process data that sort of summarizes the main important things that are being processed. So you've got the independent variable and then the average dependent variable. Notice you don't include the trials again. And then any calculated quantities or uncertainties. And there might be several, okay? So you propagate your uncertainties and you show those particular calculations a little bit later in the calculations or processing section. That can also go at the end of the method or in a dedicated calculations section. Notice that when you are propagating your uncertainties, you must use the propagation rules as outlined in the data booklet in topic 1.2 or using the range techniques to the propagated quantity. You cannot directly process the uncertainty. So for example, the uncertainty on t squared is not the uncertainty on t squared, okay? And you have to be careful about that fact. So you're expected to propagate uncertainties according to those rules. You will then have a well-formatted graph as shown here, showing the process-dependent variable versus the process-independent variable for whatever your linearization is. You can include a title or a subtitle, and you should show the equations for your maximum gradient and minimum gradient within your error bars on the graph itself. It's worth noting that right here you can note the systematic error from the correct with correct units from the y-intercepts if you can read off the systematic error. Notice that that only works if the two quantities are expected to be directly proportional. So if that y-intercept is expected to be 0, only then does that y-intercept indicate the systematic error. Notice that this analysis will depend on sort of exactly the type of uncertainty you have chosen. If you're using the standard deviation, you should estimate those gradients generously. If you're using the range, you estimate conservatively. So with the range, you really, ideally you keep those best fit lines within all the error bars. That won't always work out. But if the standard deviation is being used, you would expect about 35% of the line to lie on the outside of those error bars anyway. Finally, for the processing section, which I've just discussed before, as either calculations or processing, you should use a table or column structure. And for each calculation, you want to give the name and an example calculation, okay, as discussed in the method section above. And furthermore, sort of in this further processing, you should explicitly state the calculated gradient of the graph, even if you're about to use that gradient of the graph, with appropriate units and calculated uncertainties. So the maximum gradient minus the minimum gradient divided by 2. Give that explicitly in the form of the gradient equals whatever the value is, plus or minus whatever the uncertainty is, with the right units. Then process the gradient if necessary to obtain the desired values. So for example, for the acceleration due to gravity experiment, the gradient, g is equal to 2 divided by the gradient. And then you can use the maximum and minimum gradients to find the range for the process value. So the maximum value of g is 2 over the minimum gradient and vice versa. The uncertainty is then the maximum value of g minus the minimum value of g divided by 2. Notice there should probably be parentheses in this, but c'est la vie. Make sure you have units on all your uncertainties and that your uncertainties are all rounded to 2 significant figures. Then you find both the percentage error and the percentage uncertainty, okay, and give both. Those are explicit calculations as well. Remember that the error and the uncertainty should only be given to 2 significant figures.